Very good morning, one and all. My name is T. Rajita, lecturer in ECE, Government Polytechnic, Mamnar. I am dealing with third semester network analysis. Now I am going to discuss about the node voltage equations to solve the node voltages using CRAMERS rule. In the last class, we discussed about how to write node voltages equation. So for this, what we are doing, first we are identifying the principal nodes, then mark all nodes with numbers and names, write KCL, Kirchhoff's current law for each node with reference to reference node. So arrange the equation in matrix form. This is the procedure for writing node voltage equations. For example, see here, this is a figure. The nodes are identified V1, V2, V reference, and all branches are R1, R3, R5, R4, R2 and R6. So the three principal nodes are there and two voltage equations we can write. So this is one node and this is another node. So at first assume that all currents are leaving. So by adding all these currents at the junction is 0. So there is a two circuits already, right? So from first node V1, the voltage equation, that is node voltage equation, is V1 minus Vs by R1 plus V1 minus V reference by R2, V1 minus V2 by R3 is equal to 0. For second node, V2 minus V1 by R3, V2 minus V reference by R4 plus V2 minus V reference by R5 plus R6 is equal to 0. These are the two nodal equations. And this equation we can write, it can be arranged in another form, that is V1 into 1 by R1 plus 1 by R2 plus 1 by R3 minus V2 by R3 is equal to Vs by R1. By rearranging that nodal voltage equation, we can write like this. Similarly, this second node voltage equation, we can write it V2 into 1 by R3 plus 1 by R4 plus 1 by R5 plus R6 minus V1 by R3 is equal to 0. In this way, we got this for 1 and 2 equations. This is equation 1 and this is equation 2. So we can rearrange these two equations in a matrix form. So this is the matrix voltage 1 by R1 plus 1 by R2 plus 1 by R3 minus 1 by R3 minus 1 by R3, 1 by R3 plus 1 by R4 plus 1 by R5 plus R6 into voltage matrix V1, V2 is equal to Vs by R1, 0. So here this is the admittance matrix. So admittance matrix into voltage matrix is equal to the current matrix. So this is the last class. In the last class we discussed about this. Now we are going to explain how to solve the node voltages. So on completion of this period, you would be able to solve the equations by using Cramer's rule and solve for currents through different branches and voltages across different points in a network using a nodal analysis. So by using Cramer's rule, we can solve unknown node voltage using determinants. The nodal equations in matrix form are represented as y11, y12, y13 are the coefficients of first voltage equation, nodal voltage equation, and y21, y22, y23 is the second coefficients of second nodal voltage equation. And y31, y32 and y33 is the coefficients of third voltage node voltage equation. So this admittance matrix into voltage matrix is equal to the current matrix. See here, that is the admittance matrix, voltage matrix and current matrix. The unknown voltages V1, V2 and V3 can be found by using the equations as below. So V1 is equal to delta 1 by delta Y, V2 is equal to delta 2 by delta Y, and V3 is equal to delta 3 by delta Y, where delta Y is equal to Y11, Y12, Y13, Y21, Y22, Y23, Y31, Y32, Y3. Delta 1 is equal to first column is replaced by the current matrix and V1 can be find out from that. Delta 2 is the second column can be replaced by the current matrix and delta 3 is equal to third column is replaced by the current matrix. So by using this admittance matrix, we can calculate the V1 and V2 and V3 to solve node voltage. This is the problem. In this, we have to find out the voltages at node 1 and node 2 respective to the selected reference. That is the question it is asked, and these two energy sources are applied to this circuit and there is a resistors, and here we are identifying there are three nodes. One is see here we are identifying the three nodes by naming that the first node is N1, N2 and V reference. So the Kirchhoff law at node 1 is equal to V1 minus 125 by 5 plus V1 by 3 plus V1 minus V2 by 2. This is the equal to 0. This is the first equation. Just again I am repeating, V1 minus 125 by 5 plus V1 by 3 plus V1 minus V2 by 2 is equal to 0. These three currents, algebraic sum of these three currents is equal to 0. Now the KCL at node 2, V2 minus V1 by 2, V2 by 4 plus V2 minus 300 by 6. These are the two voltage equations here. And these two equations we can rearranging. We are getting V1 into 1 by 2 plus 1 by 3 plus 1 by 5 minus V2 by 2 is equal to 25. The second nodal equation is minus V1 by 2 plus 1 by 2 plus 1 by 4 plus 1 by 6 is equal to 50. So these are the two node equations, and now this can be arranged in a matrix form. See the equation, and 1 and 2 is arranged in a matrix form. So in this, the first equation coefficients is the first row and second equation coefficients is the second row. So here 1 by 2 plus 1 by 3 plus 1 by 5 minus half and minus half in second row, and 1 by 2 plus 1 by 4 plus 1 by 6 into voltage matrix is equal to, the current matrix is 25, 50. So this we can simplify by 1 by 2 plus 1 by 3 plus 1 by 5 can be replaced, its fractional form, that is 1.03. Means 1 by 2 is 0.5, 1 by 3 is 0.333 and plus 1 by 5 is 0.2. So by adding these three things we are getting 1.03, and minus half is 0.5 and minus half is 0.5, and 1 by 2 is 0.5 plus 1 by 4 is 0.25 and plus 1 by 6 is 1.666. So by adding all the things we are getting the matrix in this form, 1.03 minus 0.5 and minus 0.5 and 0.91 into voltage matrix V1 V2 equal to 25 50. So from this admittance, above admittance matrix, we can find out the determinant value. So determinant value delta y is equal to, we can multiply the diagonal elements. So delta y is equal to 1.03 into 0.91 minus of minus 0.5 into minus 0.5. So by solving this we are getting that 0.6873. So by using CRAMERS rule, we can find out V1 is equal to 25. The first row is replaced by the voltage matrix, current matrix, and by delta y. The first row, the first column, that is replaced by current matrix 25 and 50, and second column is as it is, that is minus 0.5 into 0.5 and 0.9. So this, by solving this we are getting that 25 into 0.91 minus 50 into minus 0.5 by delta y. So this we can get that 22.75 plus 25 divided by 0.6873. So from this we are getting that 69.47 volts is the node voltage at node 1. Similarly, we can solve for V2 also. And V2 is equal to the matrix. In the matrix, we have to replace the second column by voltage matrix. So then that is delta 2 by delta y. So delta 2 is equal to 1.03 into 50 minus of minus 0.5 into 25 divided by delta. See here, the same thing is written. And 1.03 into 50 minus 25 into minus 0.5 divided by delta. So, by solving this, we are getting 93.117 volts. V1 and V2 is easily solved by nodal analysis method. Now I am going to take another problem. See here the problem. In the circuit, find the voltage source V2 which results in a current 0 through 2 plus J4 impedance. There are the two voltage sources. In this, we have to find out the V2. And the condition is the current through 2 plus J4 is 0. And we should calculate the voltage V2. So by inspection, by seeing this voltage circuit, we are identifying that there is two nodes. So that we can, only one nodal equation is getting. See here, only two nodes, that is N1 and V reference. So the number of nodal equations is 2 minus 1 is 1. And only one nodal equation we are getting now. So by applying this KCL, Kirchhoff's current law, to N1, the equation is V1 minus 50 at an angle of 45 divided by 2 and V1 minus V reference by 2 plus J4 minus plus V1 minus V2 by 5. See here, V1 minus 50 at an angle of 45 by 2 plus V1 by 2 plus J4 and V1 minus V2 by 5 is equal to 0. It can be rearranged as V1 is equal to 1 by 2 plus 1 by 2 plus J4 plus 1 by 5 is equal to 50 at an angle of 45 by 2 plus V2 by 5. So like that we are arranging the equation. Now we have to find out the V2. But here the condition is the current through 2 plus J4 is 0. So once the current plus across 2 plus J4 is 0, then the voltage across 2 plus J4 is also 0. The voltage across 2 plus J4 is nothing but the nodal voltage V1. So once you can find out that V1 that must be equated to 0, then we can find out that V2. Because in this equation, two unknown quantities are there. But the given condition is the voltage across the, current flowing through the 2 plus J4 is equal to 0. So the current flowing through the 2 plus J4 is equal to 0 means the voltage across the 2 plus J4 is also 0. So that the V1, whatever we have to find out, that V1 must be equated to 0. So before, whatever the equation, that equation can be rearranged or reduced. V1 into 0.5 plus 0.2 plus 0.1 minus J0.2 is equal to 25 at an angle of 45 degrees plus 0.2 V2. So this we can write V1 into 0.8 minus J0.2 is equal to 25 at an angle of 45 degrees plus 0.2 V2. Now V1 is equal to 25 at an angle of 45 degrees plus 0.2 V2 divided by 0.825 at an angle of minus 14.04. So, by converting the rectangular form 0.8 minus j.2, we can get this rectangular form into polar form, that is 0.825 at an angle of minus 14.04. Because 25 at an angle of 45 plus 0.2 V2 divided by minus 0.8 minus j.2. Here this is the division. For a division, we have to convert that into we have to convert the denominator into a polar form. So that is the reason I am converting that 0.8 minus j.2 into a polar form. We are getting that 0.825 at an angle of minus 14.04. So current through 2 plus j4 is equal to 0. Then V1 by 2 plus j4 is equal to 0. So here V1 is equal to 0. So substituting the value V1 in equation 1, we are getting that 0 equal to 25 at an angle of 45 plus 0.2 V2 divided by 0.825 at an angle of 14.04. So for finding that V2 is equal to, so the denominator we can reduce because outside that is equal to 0. So 25 at an angle of 45 degrees is equal to 0.2 V2. Then V2 is equal to minus 25 at an angle of 45 degrees by 0.2. So that equal to 125 at an angle of minus 135 degrees. See why means minus means it is 180 degrees and it is plus 45. Plus 45 minus 180 degrees. So that we are getting minus 135. See here minus represents that opposite side. Minus represents opposite side. So at an angle of 45 is in first coordinate and the opposite side is the 135 degrees, that is 215. So that 215 plus 45 degrees minus 215 plus so minus 25 at an angle of 45 degrees means 25 at an angle of, we can write it 215 also. 25 at an angle of 215 by 0.2. See that there is a 215 is there means in anti-clockwise direction it is 215. In clockwise direction that is minus 135 degrees. See again I am repeating that 25 at an angle of 45 degrees plus 0.2 V2 is equal to 0. Here V2 is equal to minus 25 at an angle of 45 degrees by 0.2. So from that we are getting minus 125 at an angle of 45 degrees. So we want to remove this minus 125. So minus is, see here 125 means plus side, minus means opposite side. So minus 125 at an angle of 45 degrees is nothing but 125 at an angle of 215 degrees. So we can write the 215 degrees, that is anti-clockwise direction, and the same is at minus 135 degrees. So we can write that V2 is equal to 125 at an angle of minus 135. Hence, to become a current through 2 plus J4 is equal to 0, then V2 must be is equal to 125 at an angle of minus 135 degrees or 125 at an angle of plus 250 degrees. This is about the second problem. Hope you understand well. Now I am going to explain another problem 3. So in the below network, find the currents IA, IB, IC. Here two sources are there, 100 at an angle of 120 degrees, 100 at an angle of 0. So we want to find out the currents IA, IB, IC. See, select node 1, the reference node, that is reference node, and node 1 and reference node. So here only one equation is coming because two nodes are there, only one equation is possible. See here, only two nodes are possible, that is 1 and V reference. So this can be, we can write in, see here, this is the equation. That is V1 plus 100 at an angle of 120 degrees by 20 plus V1 by 10 and V1 minus 100 at an angle of 0 by 10. See here the current direction and IA is the current source direction and current IA are in same phase. So that we are taking that V1 plus 100 at an angle of 120 degrees by 20 plus V1 by 10, and the third case, that is the current source direction and the current IC direction both are out of phase. So that is the reason we are writing that V1 minus 100 at an angle of 0 by 10 is equal to 0. So this is the nodal equation at V1. And this can be, we can write V1 is into 1 by 20 plus 1 by 10 plus 1 by 10 is equal to 100 at an angle of 0 by 10 minus 100 at an angle of 120 by 20. So this we can write that by taking LCM. So we can simplify this. 100 plus 200 by taking LCM 2000 is equal to 10 minus 5 at an angle of 120. So this is nothing but 500 by 2000, that is V1 into 1 by 4. So V1 into 1 by 4 is equal to 10 minus 5 at an angle of 120 degrees. See here, V1 by 4 is equal to 10 minus 5 at an angle of 120 degrees. So V1 is equal to 40 minus 20 at an angle of 120 degrees. See, this is in rectangular form, we have to convert into a single. So that 40 plus 10 minus J 17.32 and 50 minus J 17.32, and we can convert into the polar form, that is 52.9 at an angle of 19.1 degrees. So V1 is in that 40 minus 20 at an angle of minus 120 degrees. In that case, we cannot add or subtract directly. So we have to convert that 20 at an angle of 120 degrees in a rectangular form. Then we are going to add that with the 40. So that equal to 40 plus 10 minus J 17.32 is equal to 50 minus J 17.32. So that equal to 52.9 at an angle of minus 19.1. So it's approximately 53 at an angle of minus 19.1. So the currents IA, IB, IC are calculated as IA is equal to V1 plus 100 at an angle of 120 degrees by 20. So this is 50 minus J 17.32 minus 58 plus J 86.6 by 20. So this, by simplifying this, we are getting that IA is equal to 3.464 at an angle of 90 degrees. Similarly, we can find out IB. IB is equal to directly, there is no voltage source here, V1 by 10. So 53 at an angle of minus 19.5 divided by 10. So that we can get that 5.3 at an angle of minus 19.1. Now IC. So IC is equal to V1 minus 100 at an angle of 0 by 10. So by replacing V1 by 50 minus J 17.32 minus 100 by 10. So we are getting this is equal to 5.3 at an angle of minus 160.9 degrees. So in this way we are calculating all IA, IB and IC by using CRAMERS rule. Now I am going to discuss another problem. In the given network, determine the node voltages at nodes 1 and 2. See, this is the figure and we are identifying 3 principal nodes here. And what are the nodes? See here, these are the 2 nodes named as V1, V2, and third node is principal node, that is the reference node, V reference. So here there is 3 principal nodes, the number of equations are 2. Now how to write these 2 equations? So the 2 nodal equations is 1 by 5 plus 1 by J2 plus 1 by 4 minus 1 by 4 and minus 1 by 4, 1 by 4 plus 1 by 2 plus 1 by minus J2. See, again I am repeating this. See here. From this V1 minus 50 at an angle of 0 by 5, V1 by J2, V1 minus V2 by 4. This is the first equation. And V2 minus V1 by 4, V2 by minus J2, V2 minus 50 at an angle of 90 by 2 ohms. So like this, these 2 equations by simplifying and put into matrix, this is the case. So this is the 2 equations simplified and put into the matrix. Now by applying CRAMERS rule, we can find out V1 is equal to delta V1 by delta V. So here delta 1 is nothing but the first column is replaced by the voltage matrix and divided by the determinant. So by solving this we are getting that there is a V1 is equal to, see here, V1 is equal to 7.5 plus J5 plus J6.25 divided by 0.45 minus J0.5 into 0.75 plus J0.5 minus of 0.0625. That is 7.5 plus J 11.25 divided by 0.525 minus J0.15. So that equal to 24.7 at an angle of 72.2 volts. So by doing these additions and subtractions, we have to convert this rectangular form into polar form If it is necessary, we have to convert the polar into rectangular form. In multiplication and division, the rectangular form must be converted into polar form. In addition and subtractions, we have to convert that polar form into a rectangular form. Similarly, V2 also we can find out, and V2 is equal to 15 plus J 11.25 divided by 0.546 at an angle of minus 15.9. So by solving that, we are getting 34.3 and 52.77. So like that, we can find out this V1 and V2 by writing a two nodal equations, putting into the matrix form, and by applying the CRAMERS rule, we can find out that V1 and V2. So in this session, we discussed about the CRAMERS rule and solving the problems to find node voltages using CRAMERS rule. So the explained use of CRAMERS rule for node analysis, generally it is frequently asked questions, and differentiate mesh analysis and nodal analysis. And any problems on node analysis. So I take the assignment. Practice writing the nodal voltage equations for different networks and solve for nodal voltage equations. Thank you.